Yes, that'd be a good idea.
Might be good.
Did you upload the previous recordings yet, by the way? I'm gonna go with
Uh,
no, but...
Uploaded one of them, not both of them yet.
Oh, we can go to campus now.
Hold up, I downloaded it again. Let me just try and upload it.
Alright.
After that, can we go over Math on a Spring? Because my computer died when he was explaining that, so I think I missed like half of it, and I'm just very lost.
Okay, yeah, we
Nice.
can do that.
Nice.
Alright.
I don't even know how to do the problem that he went over today.
Yeah, that was Math on a Spring. It was weird.
Yeah.
Alright. Is there any problem in particular that specifically for the math homework or for the physics homework, or is it all of it?
You just want you want us to go over all of it, or do you have specific questions?
Could we actually go over all of it? Because I'm pretty confused on. Well, not confused. I just want to kind of redo everything.
Yeah, because that's going to be what the test is fully on, isn't it? Past anything. So.
Yeah.
Alright.
Okay. Well, I can tell you because we have gone over the last one before. I can tell you right now that the last one is absolutely ridiculous and nowhere near close to a question that AP would ever ask you. To the point that it confused all of us who were going over it, including several people from senior class. None of us could really look at it and be like, "Oh, that makes sense."
Yeah, you had to look at it for a while in order for it to.
But anyway, we'll get there. We'll start with the first one. Let me see. Can I copy these into the board? Kind of? Yeah.
Huh. Interesting.
Cool. Alright. No, not what I want. Ugh. There we go. Alright. Alan, you want to do it, or do you want me to do it, or what do you want to do here?
I'll do it. So
Okay,
we
go ahead.
have. Looks like I'm marking the concept board right now. So longitudinal wave amplitude 2 centimeters, frequency 2 hertz, speed 3 meters per second. Child marks Slinky. How far apart are the two nearest points of the Slinky? Oh, I remember this question. Okay, so here we have, and this is longitudinal. So we have. Does anyone remember what a longitudinal wave looks like as opposed to a transverse wave, or do I need to clarify that?
Could
I
you
think we're
clarify?
good with that. Like, that's the basics. It's just it goes up and down.
Yeah.
Yeah.
So really quick, just a transverse wave is when it makes like the waveform, like when the individual particles move up and down or left and right. For transverse, they're moving in the perpendicular to the way the wave is moving, and for longitudinal, it's moving in the same direction as the way the wave is moving. So like if you think of holding a slinky in both, or two people holding a slinky and then shaking it up and down, that's a transverse wave. If you think of it like pushing basically into the slinky and then pulling it back out, you'll make longitudinal waves traveling down the slinky. And so for here it's longitudinal, meaning that the particles move in the direction of travel, meaning that your displacement between them will be changing. So for this we have amplitude 2 centimeters, so that means that when you have one particle, it will be moving, its maximum displacement from like its neutral position will be 2 centimeters forward or 2 centimeters backwards. You have your frequency, which is just the number of times a wave goes by in 1 second. And then you have your speed, which is just the speed of the wave. So for this, if I'm remembering correctly, because it's been a bit since I've done the wave ones, it's, oh god, let me look it up. I have my formula sheet here. It's where is the, does anyone have the equation that's like it's like
Formula sheets and notes resources. I don't know if
notes
that's what you're
resources,
looking
like
for.
an actual document?
That's a link to the document.
Sure is. Alright, let's do that. So it's like what, lambda equals, wow, It's taking me forever to find this. Hold on, give me a minute.
Are you looking for a wavelength is equal to
Yeah.
velocity times period, or velocity
Yeah.
over frequency?
Yeah. Where is that on the sheet?
If it's not on that sheet, you might just have to memorize it. I haven't looked at that sheet in a while. Let me see if it is on there. But I mean, you can use dimensional analysis, right? So you know wavelength, lambda's wavelength. You know velocity is meters per second, so you have to cancel out seconds. So your options are either multiply by seconds, which is multiplying by period, or divide by 1/seconds, which would be dividing by the frequency.
Right. So you have your amplitude, which is meters, is amplitude. Frequency, which is 1/seconds, and then you have your speed, which is 3 meters per second. But an important thing is this speed, even though it's 1 meter per second, is not the same as these two multiplied together, because the speed is the speed of the wave, and the meter here is the displacement of the particle. And since you're trying to find maximum displacement, you're looking for wavelength, which you want to get by multiplying. Which you want to get by dividing this by your frequency, because it's 1/seconds, and that would cancel out. So you have m/s times the inverse of 1/seconds, which is just seconds. 1, these cancel, and you're left with meters. So for this, you just do 3. Nathan, actually need so for this, you have 3 meters per second, so you do. I cannot draw. You have. Oh, I'm off the screen. Was it here? Yeah. Okay. So we have 3 meters per second times. Oh no, it would be divided by. So it would be times. Up 1/2, so times 1/2 equals 1.5 meters. That's not a 5. 1.5 meters. 1.5 meters. So that's your wavelength. And for this problem, you want to find the wavelength is the distance from, like, in between, the two same parts of the wave. It's like it's the length of one full waveform. So the parts that have the maximum displacements from the equilibrium positions is going to be half the wavelength apart. And that's going to be like when both of them are moving. This is one of the questions that I remember us talking about, that it depends on how you interpret the question and what your answer is.
Yeah. So the one place where this question is ambiguous, it's a small place, but it would completely change your answer, is when it says how far apart are the two nearest points in the Slinky that both have the maximum displacement. It doesn't specify if it's saying their original position or if it's saying their displaced position, which wouldn't matter if it was transverse, but it's explicitly longitudinal. So the question changes if it's asking their displaced positions or their initial positions. So we can solve for both, but did you guys ever talk to him about which one he meant, or
I think the answer he gave was the one assuming their neutral positions, not their displaced positions. He said,
then just do their initial positions, which is actually a lot easier.
Cause if it's just their normal positions, if you think about a waveform, I have to draw a waveform real quick. You can move down the camera real quick, Nathan. If we draw a waveform, just really quick, we'll just draw a sine wave. It would be just here. And this is just a transverse wave right now. One wavelength is from here at the beginning to here. And if you look, you can see that the closest points here are here and here, which on a sine wave you can't really tell. But on a cosine wave, which is down a little bit further, it starts at its highest point, goes to 0, down, back up, and just continues. So here, your close one wavelength ends here, and the closest points are here at the beginning, and here, which drawing isn't the greatest, but you can see that it's basically just the middle of it. So you take half your wavelength, which is 0.75, and that's your displacement between the 2 points of the maximum displacements. If you needed to find them with their displacements, this one would be like, I think the displacement here was 2 centimeters. This would be plus 2 centimeters. Let's do plus 2. And then this one down here would be minus 2. So you would essentially take 0.75 minus 0.04, because you have them moving towards each other, 0.02 meters each, which is just 2 centimeters. So you would have so your final answer would be 0.71 meters distance between them. That's a better graph showing it, yeah. Because you have it starting at cosine, and then it goes down and up, and that green line is the length of like a full wavelength, and then that blue line is pi, because you measure your displacement with waves by pi. We'll explain that when we get into simple harmonic motion, because that'll be an easier time to explain it, I think.
Also, Alan, I just gotta ask, you're recording this, right?
Yep, I'm recording it.
All right, pretty good.
Okay, so just to be clear, that was a very in-depth answer. Although the question itself, like we said, is just half of the speed over the frequency. So just so we're all on the same page, even though we're trying to explain what we did to get there, the question itself is not that long. Assuming he meant the origin position. If he meant displacement position, that's more complicated.
Yeah, of course. So if we then look at the second part of the homework, second problem on the homework.
Well, before you move on, does anyone have any questions about this one? Everyone understanding how we got that and why it's half the wavelength?
Okay. Michael, you got anything?
Can you explain why you have to have the speed, please?
Yeah. Well, it's not necessarily having the speed; it's having the wavelength.
Yeah.
It just, when you're multiplying everything, it's halved at the end. But basically, if you don't mind, can I draw on?
Yeah, sure. Go ahead.
Okay, so I'm gonna use the graph here. Right. So imagine that this is our wave, and we're saying that if we have our slinky. So it would look like these there, then the slinkies get closer together, then they get farther apart, then they get closer together, then they get farther apart. Okay, so this is our slinky. So this is our x direction.
The longitudinal wave, remember, it's your points of, your points where you're closest together depend on where you are on the waveform. So you're furthest apart when you have, because of it, you have positive behind and then negative in front. Meaning that it's moving forward, then backward. So on the first point where it goes to 0, that's where it gets close. But on the second one, you have it moving backwards and then moving forwards. So that's the part where it's farther apart. On that 0.
Yeah, well, it's closest together here because these ones are all moving forward.
Not on the next one. The next one would be further apart.
Oh yeah. You're right. Whoops. I'll redraw. So over here, closer together, and then over here, farther apart.
Yeah.
All right. So over here, so if you imagine this is our slinky, high quality. This is the x direction of our slinky, and the y version of our graph just shows you the displacement of the particles there. So we're saying whatever particle is normally at x equals 0 is now really far down this way. Over here we're saying the particle that's normally here is a little bit down that way, and over here we're saying the particle that's normally here is still there. Then over here we're saying the particle that's normally here is a little bit that way. The particle that's normally here is all the way that way as far as it can go. The particle that's over here is a little bit that way, and the particle that's here is still here. So because of that, when it says maximum displacement, so remember that one full wavelength is starting from one particle going to the same displacement in the same direction. So if we started our waveform here, where this particle is displaced all the way this way, then it's going to end at the next particle that is displaced all the way that way at the same point. But there's another particle in between them, which is displaced as far as it can go, but in the opposite direction. And that's always going to be, halfway between a full wavelength over here, because you're going to go all the way this way, smaller, smaller, and you're going to grow in the other direction. And so you're all the way in the other direction, and then you're going to, get smaller and leap back until you're all the way in the original direction. So because it just said points of maximum displacement, there is, if you start with the first point of maximum displacement, your second point is going to be half a wavelength away than where you started.
Does that explain your question?
Yes, thank you.
Alright, no problem. So, now we go to question 2, which is large goose lands in a lake, bobs him down for a short time. Wishman notices that the first wave created by the goose reaches the shore in 8 seconds. Distance between the wave crest is 80 centimeters, and in 2 seconds he sees 4 waves hit the shore. How far from the shore is the goose? I remember there being an issue with this one too. This seems to become a common theme. Because it depends on if you're measuring the wave crest. We'll get more into it once we actually solve the problem, actually.
It's 4 waves, because I think I did it with 4 waves and I got it right.
Okay. Good. So we have large goose lands in a lake, bobs him down for a short time. We should notice that the first wave reaches the shore in 8 seconds. So our 8 seconds here isn't a period, nor is it a frequency or something like that. This is just a time taken. So we'll just keep that there for right now. Just keep 8 seconds in our heads. Distance between the wave crest is 80 centimeters. So 80 centimeters is our, I'll do this in blue. 80 centimeters is our wavelength here. Because if you think about it, and if you're thinking about a wave on water, you have your high point, and then it goes down, and it goes back up to your high point, and that would be one full wavelength. And then in 2 seconds, 2 seconds here is our period, or not? No, never mind. 2 seconds here is still not our period. 2 seconds is the time it took for 4 waves to hit the shore. So we have 2 seconds, and we have 4 waves over 2 seconds. So if we do 4 divided by 2, we get 2 waves per second, which would be our frequency. So we'll do 2 hertz. Even though, and hertz is really just 1 per, it's just over, it's just, yeah, it's 1 over seconds. So this is 2 hertz, so 2 waves per second. Then how far from the shore is the goose? Well, if we go back to if we think with this, with dimensional analysis, we have a second here. No, we need a speed. So first we have hertz, which is 1 over seconds. We have distance between the waves, and we want to find the speed that the waves are traveling. So we do dimensional analysis. We have 1 over seconds times a distance, which will be in meters, equals meters per second. So for this, we're going to be doing 1 over seconds, which is 2, times 0.8, because it's 80 centimeters, equals be 1.6. So 1.6 meters per second is the speed that the wave is traveling. Okay. And then how far from the shore is the goose? We just take this, which is meters per second, and we can say, okay, it's 1.6 meters per second. We have seconds. We just multiply it by seconds, and we get the answer. Meters per second times 8 seconds, and then that cancels out the seconds here, and you get total of, I have to use my calculator real quick. 1.6 times 8 would be 12.8 meters. I think it's just on the screen. Okay. Does anyone have any questions about that?
Yes.
Okay.
Why'd you put point 0.8?
0.8. So, if you want to find your velocity in meters per second, which it makes everything easier if all of your stuff is in the same units. So like meters per second, newtons, that kind of stuff. Instead of having some that's like millinewtons, if there's stuff like that, or centimeters, that kind of stuff. So changing centimeters to meters, you divide it by 100, and here that just changes our 80 centimeters to 0.8 meters. Does that make sense?
Yes, thank you.
No problem. Any other questions?
Are there any questions about how we got that?
Going once, going twice.
Well, actually, yeah, I have a question. Can you just go over again, like, why you determined that you had to use velocity to find how far it was?
So, for this, the only distance we have is our wavelength, and with the variables we're given, there's no way to get a different distance other than using dimensional analysis. If that makes sense. Like with the wave equations, the only way to really get a distance traveled by a wave is to use the wave speed and multiply by time.
Alright, I get that. Thank you.
No problem. Okay. So, assuming we're going to move on to question 3. I'm assuming there's other questions. We have quickly copied over. Oh, I can beat you to it. Okay. Radio waves travel at a speed of 1.7 times, is that 10 to the 8th meters per second? Yeah. 10 to the 8th meter per second through ice. Radio wave pulse sent into the Antarctic ice reflects off the rock at the bottom and returns to the surface in 32.9 times 10 to the negative 6 seconds. How deep is the ice? So this is just another, it's actually pretty similar to the last problem. It's just, instead of trying to find, actually no, it's basically the exact same as the last problem. It's just given in really different numbers. So you have your wave speed, which is, we won't actually run that, we'll just do it using scientific notation. So we know that we need to find a distance, and of course we are given a speed and we are given time. So if we want to find a distance, we want to multiply the speed by time. But here we have to be careful because we want to know how deep the ice is, and we're finding the amount of time it takes for the wave to travel all the way down and all the way back. So when we find our answer, we're going to want to half it to make sure we account for that. So we've got, this is going to be easier just doing a calculator. I can try to draw it out, but it's really just going to be 1.7 times 10 to the 8th, and that's meters per second, so I'll write that up here, times, that's weird how it's done, is it really 32.9 seconds? Just making sure I'm not reading that wrong. Yeah, that's weird. I don't know why they would, if you're going to go through the effort to put it in scientific notation, why wouldn't you just do it in, at that point, to 10 to the power of negative, what would it be? 5? I don't want it to be scientific.
Yeah, it should be 3.29 to something like that, but yeah, we don't question these things.
It's, yeah. Let me do times 32 point, 32.9 times 10 to the negative 6, and that's seconds, so seconds cancel, and we get meters, which I gotta do this real quick on my calculator. So 1.7. 0.7 times 10 to the 8th. If someone's faster than me at solving this, just go ahead and tell me what it is. This is going to take a minute. So 10 to the 8th times 32.9 times 10 to the -6th, which should give us 5,593 meters. I wish I had something to background that off, if anyone's calculated it out themselves. I want to make sure I don't mess up just the numbers here. Is this text box works? Oh, that'll be perfect. Just do enter and that saves it. Let's click off it. There we go. That'll be way easier for the numbers. Oh, I have to. There we go. 5593. So I think, as far as as long as my basic math is correct, which it's always a toss-up, that's the distance we got. But remember, this is finding it. That is assuming that it was traveling in a straight line the whole way, basically, because you're given a time taken. You're given the time taken to reflect off the bottom and come back. So this distance is assuming it was traveling in a straight line the whole time, but really we went down and back, so it should be half of this. So 5593 divided by 2, and we go 2796.5. So that
I can't confirm I got the same numbers.
okay, just making
so
sure.
we're on that same page.
You never know. Oh. There you go, 2796.5. Does that make sense to everyone how we got that? Any questions? Going once? Going twice? Okay. So, moving on to the next one, we have noise of thunder is heard 3 seconds after the flash of lightning. So I'll quickly paste in here. We'll move it here. Noise of thunder is heard 3 seconds after the flash of lightning. How far away is the place the lightning struck? Speed of sound is 10 meters per second. So again, we can just use noise analysis and realize that we have a speed, we have a time, so you just do one, I'm assuming we're just going to say that the speed of light is instant here, because I don't think it shouldn't affect this problem, given the fact that there's still like 8 orders of magnitude different. So we have,
Yeah, since it only gives you speed of sound, I'm assuming it's saying the speed of light is
so
instant.
300, that's not a 0. 340 meters per second times 3 seconds. Seconds cancel. You have 340 times 3. 1020 meters total.
So what you'll notice is a lot of these questions is pretty much looking at your units and figuring out how to cancel the right ones to get what you need.
That's most of waves besides the harmonic motion.
Yeah, for waves outside of harmonic motion, the trickiest part is going to be making sure you don't combine two numbers that have the same units but can't actually be combined. Like if you're trying to use wavelength in a transverse wave somehow with your x-axis, like that isn't going to work, even though they're both in meters. So just be very careful about what numbers you're using. But overall, almost all of waves is pretty much how can we use the numbers we have with the units they have to get what we need.
Okay, and then any questions? Going once, going twice. Okay. So, next one, we have water wave crests in a lake are 5 meters apart and pass by an anchored boat every 2 seconds. What is the speed of the water waves? We will do this one just below here because there's a lot more space. So, we have water wave crest and lake 5 meters apart. So we have a distance already, and that is a wavelength here. And pass by an anchored boat every 2 seconds. That's our period. What is the speed of the water waves? This is again just analysis. You have a distance, you have a time, you know that you need to get a velocity, which is meters over seconds. So you do 5 meters times 1 over 2 seconds equals 2.5 meters per second. Make sense to everyone? Any questions? Oh, Michael?
Nothing. That was by accident.
Oh, okay. Alright. Alright. Going once. Going twice. Okay. So, moving on to number 6. Sound wave of frequency 450 Hertz is emitted from A and travels towards B, a distance of 150 meters away. How many wavelengths fit within the distance from A to B? Okay. So this problem is actually quite a bit more complicated than what we're used to. I'm going to move over here because we're going to need a lot of space for it. So, we have sound wave of frequency 450 Hertz, so that's our frequency already. And if you want to move the camera over a little bit, just so it's like at the top left of the camera view. Yeah, okay, thank you. Sound wave of frequency 450 Hertz is emitted from A and travels towards B. Is 150 meters. So first, immediately we have 150 Hertz, and that's 450 Hertz, and that's 1 over 450 seconds is the period for that, because you can just interchange between them. So we have 1 over seconds, we have a distance, and we need wavelengths. Speed of sound is 340 meters per second. So that is our speed then. So we have 340 meters per second. We have 450 Hertz. We have 150 meters. This is one of those points where you have to realize that just because you're given a distance doesn't mean that it's your wavelength here, because here your wavelength you'd have to do using the speed here, which is what we're gonna have to do to solve for wavelength, because of course we have a distance. So if we take the 340 meters per second for the speed of sound, that would be 340. That's not a 3. 340 meters per second, and we have frequency 450, so that's 450 would be, of course we don't want acceleration, because that'd be, if we multiplied them, that'd be meters per second times 1 over seconds, so that would give us meters per second squared. If we instead want a distance for our wavelength, so what we want to do is we want to do 340 meters per second times 1 over 450 Hertz, which is really 1 second over 450. Just flipping them around, and then we have equals 340 divided by 450, which would give us 0.5 through repeating. That's probably a nice fraction. I had to guess. Yeah, 8/15ths, but of course that's not very useful when you're doing it in a distance. So our wavelength is, we'll just do 0.53 for right now. And I'll write that using the text, it's easy to read. So we have 0.533 here. Well, this is 0.533. We need to find how many wavelengths fit in the distance from A to B. So this is basically just, you have 150 meters, and then you have, oh, that's wrong. That's not 5.33. It's 0.533 meters. Hold on.
Alan, why'd you do 15 over 450 again?
It's not 15. It's 1 second.
Oh, okay. I was confused there.
Yeah. Hard to write with a mouse. There we go. That should be better. So you have 1.5. 1.533. Let me just add a meters to this. That way that's also. We don't mess up our units. 1.533 meters, and then so then on top of that, we have, of course, our main distance here, which is 150 meters. So we know we have wavelength of 0.533 meters, and we need to find out how many of those in 150, and that's just, you know, basic division of how many of this goes into that. So 150.
Alan, is your 5.533 supposed to just be 340 over 450?
Yeah.
Then you should probably do that again, because it's I'm not getting 0.533.
Did I do it wrong? Oh, I did 240. I'm smart. Always check your operations, because you might just be stupid. You'll never know unless you check your operations. Okay. So 0.756. So 0.756 meters. Okay. So 0.756. You have your distance of 150. So you just want to do 150 divided by 0.756, or yeah, and then that would equal 50.756, give you 198 wavelengths, approximately 198.41. Nathan, could you double check my math? Make sure I didn't mess that up.
Yep, that looks good.
Okay, so then, I know I had a little bit of difficulty explaining that one. Anyone have any questions? Really? No questions? Oh wow, okay. Man, you guys are getting this fast then. Okay, going once, going twice.
I mean that, or they're all desperately confused and don't even know what questions to ask.
Right, I'm assuming it's not that though, because they've been doing really well so far.
No, I think we're actually we get this.
Oh, well, that's good. That's good.
All right, that's good. Good stuff. Oh, by the way, Alan, I don't know if you saw my message, but if you go to the top right where there's a little projector icon, click that.
I hit start moderating.
Yeah, and then you can.
So then I can move around the projection.
Yes, just move your screen while you have that open.
Oh, look
And
at that,
see,
it does.
moves.
Cool. Okay. So next one we have radio station emits a frequency of 90.8 megahertz. What is the wavelength of the waves emitted? So this one, there's another hidden variable in here that isn't actually written, and that's the speed of light. Speed of light. Speed of light is, quickly type it out here, is 3 times 10 to the 8th meters per second. And that's just a value that you kinda, I'm pretty sure it's in the formula sheet, but it's also not that hard to memorize, because it's just 3 times 10 to the 8th. It's not that long compared to stuff like, other constants that you're in your formula sheet.
It is in the formula sheet though, just to.
Okay, well then you're fine. Doesn't matter. So here you have a speed, or a velocity, I should say, and then you have a frequency of 90.8 megahertz. This is the part my memory is going to fail me. Megahertz is to the 8th, right? I think that's
No, it's to the 6th, and this stuff is also in the
also in the
formula packet first page, where it says prefixes.
So this
Mega
is
10 to the 6th.
Yeah, so what this is actually is I'll type this one out too. This is 98,000,000 hertz. That's actually what this is. It's just they wrote it as megahertz because then it looks nicer. So now we have our speed, which is of course meters per second. And then we have our 1/second, so we're going to divide it by our frequency, which so we're going to multiply by our period. which is just going to be 1 over 908. It's just going to be a really small number. And that will give us our distance, which will be our wavelength. So we'll do 3 times 10 to the 8th divided by 908 0, 0, 0, 0, 0. That's 5 zeros. And that should give us 3.3 meters, which is about right for a radio wave. Yeah, radio waves are typically around, hundreds to tens of meters. So this is not far off. So we have 3.3. Okay, so we have 3.30, we'll just 3.304 meters is our wavelength here. Okay. Do we have any questions?
Yes.
Alright, what you got?
How do you know what to plug? I don't know how to say it correctly. How do you know what goes into what when you plug them in?
So, yeah. So for this, it's really following the same, like, process as we were doing earlier. You take the values you're given, which for this is you have your frequency, which is 90.8 megahertz. You have your speed, your wave speed, which is 3 times 10 to the 8th meters per second. And you need a distance. And for this, there is a specific equation on the formula sheet that I couldn't find because I can't look very well. But it's basically wavelength equals wave speed times seconds, because that will cancel out and give you wavelength.
So the equation on the formula sheet is actually wavelength is equal to velocity over frequency, which is the same, of course, as velocity times period. But it just they only give you one of them, which is velocity over frequency. So just remember, since 1 over frequency is period, velocity over frequency is the same as velocity times period, or times seconds in that case.
It's just I don't know if everyone here is. I'm pretty sure most people here are AP, but if there's anyone who's IB, doing it this way means that I don't use symbols for either. I use a lot fewer symbols that wouldn't be shared between them, so that way it's easier to understand. That too.
What do you mean by fewer symbols? I think I'm the only one who's an IB here.
Okay, yeah. So IB uses their own. IB and AP use their own notation. So for you, your displacement is measured in. It's S, right? Is displacement?
Yep, it's S.
Yeah.
I think so.
Yeah. So in AP, displacement is measured just by X instead.
I mean, the general is just that it does two things. One, it allows us to explain it in a way that we don't have to say, okay, AP people look at this part and IB people look at this part. We can just explain it in one way. And two, it sort of gives you an understanding of what the equation is, as opposed to just, here's an equation, use it. Because really that's where that equation comes from. It's just the fact that, meters over 1 over seconds works out to meters. Or sorry, meters per second over 1 over seconds is equal to meters.
Yeah, because, I'm going to be honest, we haven't worked out a single problem dealing with waves yet. Today we went over what longitudinal waves were. So I'm just kind of following along with what you're saying, and, to me, are a lot of these just going to be, dimensional analysis, basically?
Pretty much for waves, yeah.
Yeah. So wait, do you guys have a test tomorrow as well, or no?
No, our test is going to be on, I think, Thursday next week. Anyways.
Okay.
Yeah, so I'm just listening.
Yeah, so we're doing this first. I think after this we're doing harmonic motion, and harmonic motion isn't on the IB test. I don't think he'll go over it. So past that point, I don't think it'll be any material you will be covering. But
Okay,
also, what'd you say? I couldn't really hear you.
I have a bio test tomorrow, so I might have to leave a little early. Then.
Oh, that's fine.
Yep, that's fine. But yeah, also, in case it's important, the equation IB gives you, for some reason, is velocity is equal to frequency times wavelength. So there's that.
So next problem we have is, what is the period of a 60 hertz electromagnetic wave traveling at 3 meters per second? Wait a minute. Well, one, this problem doesn't make sense because electromagnetic waves always travel at 3 times 10 to the 8th meters per second. So I'm assuming he put an electromagnetic wave just to throw people off. So if we're just treating this as a regular wave, it would just be 60 hertz, so that's 1 over seconds, and then you have a speed of 3 meters per second. Then you want to solve for distance, so you do 60 hertz. Let's do that a little bit better. 60 hertz, which is 1 over seconds. 60 over s, and then you have your speed, which is 3 meters.
Alan, read the question again.
What's it? You're finding period. Oh! Ha! I did the stupid where I thought we were solving the same thing again.
Yeah, so he definitely put in electromagnetic just to trip people up. There's no reason both the words electromagnetic and 3 meters per second should be in there. In fact, having them both in the same sentence makes the question impossible.
You need nothing from this problem past the point where it says period of 60 hertz. All of the rest of this is irrelevant. You now know period of 60 hertz, that's 1 over 60. That's your answer. 1 over 60 is just your answer for this problem, because period is just the inverse of frequency. Because it's 1 over seconds, and then you're converting it to seconds, which is period. Any questions?
Is the period always going to be the inverse of the frequency?
Yep.
Okay.
Always.
Thank you.
No problem. Okay, going once. Going twice. Okay. Now, next problem. We have next one, which is here. If the amplitude of a wave traveling in a rope is doubled, what is the effect on the speed of the wave? This is another one where you don't need to do any math. You can just think about it and you'll figure it out. Amplitude is just moving. It's a rope, so ropes can't really compress. You can't really have a longitudinal wave in a rope. So this has to be a transverse wave. And if you have amplitude in a transverse, actually in any wave, in any wave, amplitude doesn't affect speed. What affects speed is wavelength. So here, it just doesn't have any effect. The wave has the same wave speed.
Actually, just to clarify that a little bit more, you made a bit of a mess up. There's nothing actually that affects wave speed except for the medium it's traveling through. Wavelength and frequency and period and amplitude does not affect the wave speed. You can calculate it using those things, but changing any of those things in the real world, if it's in the same medium, it's going at the same speed.
Alright, we have any questions? Going once. Going twice. Okay. This is the last problem. This one is... how do I best say this? Interesting.
I mean, for context, me and Alan were very confused, so we showed it to like 3 or 4 other people who were in, IB Physics last year, and we're all like, what the heck is this?
And to see if it's going to paste properly, it's just going to crash my browser or something. I tried to paste it in here, I think it just didn't. Okay. Nathan, if you want to... it gives you an equation, which I will attempt to paste in general.
No, I'm just going to paste the image.
Yeah, no, it literally doesn't paste. Okay, because it's using orb stuff. Okay, so for this, I think the best way to explain this is to pull it up in Desmos.
Yes.
So if you want to pull that up, Nathan.
I will do that.
Yeah. So it's if you look at the equation, it's y equals 14.0 m cosine, and then in brackets 2 pi, and then in parentheses 0.33x plus 2t parentheses bracket. There's a lot to talk about here. I think first we can kind of just ignore the m, because I had to guess like m is just like slope here. or that affects what the amplitude is, specifically with this. And we can, for right now, to simplify things, just act as if it's not there. Then we have cosine, so this is going to be starting at a peak. And then this is the strange part, is it's cosine 2 pi, and then in parentheses, 0.33x plus 2t. And if you look on the, so if we look here, we have m, which if you move it around, Nathan, we'll just make it taller or shorter. So that just changes your amplitude. But if we look at the first question, it's longitudinal or transverse. Initially, when Nathan and I looked at this, we thought, how do you tell? It would really look the same. But if you, because you can tell because of one factor, it has t in the equation. And if you drag t back and forth, you can see that the wave is actually moving. So as you increase time, it goes to the left, and as you decrease time, it goes to the right. So for this equation specifically, it is a transverse wave. Amplitude. The amplitude here is what you're, of course, it's the highest or lowest on this graph it can go, and that's determined by the 14.0 m times cosine, because of course the maximum of cosine is 1 or negative 1. So your amplitude will be 14m. Wavelength. It gets a little bit more complicated at wavelength, because you have your 2 pi times 0.33x, and one wavelength will be once you hit the same point, which in this graph will be, you can see it has a peak, which goes to a trough, which goes back to a peak, and it's very tiny just after the origin. And that's your wavelength there, which, if you can zoom in, Nathan, I think we can see actually just what it is. I think it should be, it's, yeah, 3.03.
So the way you essentially have to solve that is you just set t to 0, which essentially just cancels out this part. So you end up with 2 pi 0.33x. And so you want to find the point. So if you remember, if you know anything about cosine, in fact, I'll just put on cosine for a second. If I can type. All right. So a cosine function is at the same value at 0 as it is at 2 pi, right? They're both 1. So what we want to look for is, when does this thing become a value that ends up being the same in cosine? So we can start with 0. So if t is already 0, then an x of 0 is going to make this whole thing 0. And the next time that the cosine is the same as the value it was at 0 would be when it's at 2 pi. So what value of x makes this whole thing 2 pi? So you just solve 2 pi times 0.33x is equal to 2 pi. That becomes 0.33x is equal to 1 divided by, so it's 1 over 0.33, and 1 over 0.33 is 3.03. Again, this question is ridiculous and will never appear on the AP or, quite frankly, IB tests, but we're rolling with what we're given. You can continue.
Yeah, and I know this is all going pretty fast, and you probably have at least a couple questions. But as long as you understand the basics of what we're doing, maybe not exactly what's happening, you'll probably do fine. I really don't expect anyone to give you like a wave equation, like a cosine or sine equation, and expect you to be able to pull all these things from it. I never had to do this in any of the tests. So, next value we need to find is frequency. Frequency is, of course, you see that t in the equation. And the frequency is, of course, how many waves go by in 1 second. So the difference in between 1 or 0 and 1, how many waves go by. And because of the fact that it's 2t, if you change it from 0 seconds to 1 second, and that of course will be multiplied by 2 pi, and 2 pi will be 1 full wave. So it's 2t, so 1 times 2 is 2, times 2 pi would be 4 pi, and that would be 2 full wavelengths over 1 second, which would be 2 waves. So that would be 2 waves per second, so 2 hertz. And then your period, this next one, is just the inverse of that, so it's 1 over 2, 1/2. Velocity is weird. I don't remember. How do you get it from this?
Now, velocity, you just use the previous things. You know the frequency,
Yeah.
or you know the period, and you know the wavelength, so you can solve it.
Just wavelength divided by period.
Wavelength over period. So you just use the previous two answers to solve that one.
Polarization was the part where we literally just threw our
I want
hands
to
up
skip
in the
that
air.
one for a second. Just do H.
Yeah.
Do
Okay.
H first.
Direction of travel, axis, and direction. So axis, I'm gonna go on a limb and just say it's the x-axis. And if he doesn't accept that, I'm gonna be very confused as to why, because that's the way the wave is moving. And direction is positive. No, negative.
No,
sorry.
it's negative.
Yeah, it's negative because if you increase time, it moves to the left. You look at it. And then
And yeah, polarization. Like I said, we all kind of threw our hands up in the air on that one. Honestly, one of you guys needs to ask him what he meant or tell us because, well, first of all, polarization is an IB-only topic for starters. And second of all, there isn't a good way to know from the equation he gave you what that is. Like, you have to make an inference that is not necessarily logical.
yeah, like because the way polarization works is using it's too much to just quickly explain in a sentence, but it only happens in light waves, practically. And there's no way to tell if this is a light wave by looking at it. So, who knows, basically.
So what we're saying is, pray you don't get this on the test. And if you do, we need to ask him like what the heck does any of this mean? Because again, there's no actually way. Like with the information given, you can't solve everything he's asking for. Trust me, we asked a lot of people who were in the class before. I was tempted to email Mr. Noble, though I didn't. But yeah. If anyone at some point asks him what he wanted for that answer, let us know, because I'm genuinely curious. But if I got this on a test, I would just say linearly polarized. Like I wouldn't know how to answer it.
Yeah, I would have no idea. Of course, it's kind of demoralizing, but yeah. Do we have any general questions?
Yeah, I have one.
Okay.
So, like, let's say you're given just a wave, like a picture of a wave, and it asks you whether it's longitudinal or transverse. Are you, like, how are you supposed to know that? Is it just, like, if it's longitudinal, does it have a rarefaction and a compression, and then if it's transverse, it doesn't? And it's just kind of like a constant...
Okay, so the important part here is if you look at the graph that Nathan has right now, that cosine graph, that is what a transverse wave will look like, always. The longitudinal wave will have those rarefactors and compressions. Like
so to be fair, right, that's not always true, because so if they give you a squiggly line and with no other context, and they say, what wave is that? It is, by definition, it's impossible to tell. What you need in addition to that is some sort of context or some definition of your axes, right? If they labeled your axes both displacement in the x direction, for example, then you know it's longitudinal, because longitudinal wave travels in the direction of motion, so both displacements would be in the x direction. If it was, like in this case, it was labeled as y is equal to, and then they used x, so your y-axis is most likely displacement in the y direction, and the other one is displacement in the x direction. It's most likely transverse. If they drew one with rarefactions, then what they're drawing is sort of the final state of the particles, and then it's always going to be longitudinal. But if they just draw a squiggly line like what you see on Desmos and ignoring any other details, it could be both, because it could be showing you the displacements of a longitudinal wave, and there's no way to know.
That's true. I think it's fair to guess that if they show you like what is essentially just a cosine graph, that it's probably transverse. Unless, but you do have to pay attention to your axes if they give them to you. Because if the axes is x is on the x-axis, and then you have change in x or delta x on your y-axis, then that is a longitudinal wave, because it's showing that you have your, as you go further down the wave, basically, the particle that's supposed to be there is moved further back or further forward based on how far you go, and that is a longitudinal wave by definition.
And a cosine graph is when it like begins at a peak? Is that what you said?
It doesn't matter if it's cosine or sine graph, but just like that kind of a graph with a cosine or sine equation.
Oh, okay.
Like just that shape.
Thank you.
Okay. Any other questions? Because I was told that I have to go eat, so I have to go real quick now. But I can be back on later. We still have some more questions after that.
Actually, to do harmonic motion. Well, before Alan goes, who here definitely needs help with harmonic motion?
Me.
I do definitely.
Me too.
All right. Well, obviously this is getting much longer than a normal session, but we all need help. Do we want to maybe how long is it gonna take for you to eat, Alan? Estimate.
It shouldn't take it'll be like, I'd say like 15-20 minutes.
All right. Do we want to take a short break and then come back and do harmonic motion? Is that okay with everyone?
Yes.
Yeah, that works.
All right. Cool. So we'll join back here in like 20 minutes. So it's 5:37. So like almost just join back by like 6.
Yeah.
That'll be fine.
6 will be fine.
And we'll go over harmonic motion and any other questions.
Okay.
Sounds
Alright,
good.
see y'all in a little bit.
I
Alright.
have to dip, unfortunately, so I won't be back. But thank you so much.
Alright. No problem.
Yep. No problem.
Peace out, guys.
Oh, he left.